Okay, so entropy change and gas expansion. Let's think through how this works. So let's imagine, to make it simple, it turns out that it ends up working exactly right, but let's make it simple. Let's say that we divide space up into boxes again. And so each molecule can occupy a box. You know, it's ideal gas, so we could say that, you know, they don't interact with each other, so they can all occupy the same boxes. So if we have 100 boxes, then even if there's like 3 particles in the system, then each particle can still occupy 100. It keeps the mass simpler. You know, with ideal gas, they're not supposed to occupy volume anyway. Okay, so now let's say we expand to a larger number of boxes. Let's say we double the number of boxes. What's the change in entropy in that case? Well, yeah, so each molecule takes up 1 unit in volume. And how many states are available if we increase the volume from 10 units to 3 units? Well, each molecule has 3 times as much room to move around as it did before. So for each molecule, the density of states is tripled for each molecule. But each molecule is moving around independently. And so you can imagine we have sort of like a density of states for particle 1, a density of states for particle 2, a density of states for particle 3. And if we triple the volume, all of a sudden, this is going to be multiplied by 3, right? So it's going to be multiplied by 3. So the overall density of states increases by, it's going to be 27 times the old density of states, the new density of states. So the number of ways they can arrange is tripled for each molecule. So we triple the first one times tripling the second one times tripling the third. So what would we see as the entropy change when an ideal gas at 30 degrees C in 1 atmosphere expands at constant temperature from 2 liters to 10 liters? And what about going backwards from 10 liters to 2 liters? Okay, it's an ideal gas, so N is equal to PV over RT, which is 1 atmosphere, 2 liters, divided by 0.08206 liter atmospheres per mole Kelvin, right? We're using this gas constant now because we're using it in the ideal gas law. 303 Kelvin, plug all that in, liters cancel, atmospheres cancel, Kelvin cancels, and so we get 0.080 moles of gas. All right, so the change in entropy, that's the first part. We know the number of moles of gas. The change in entropy is going to be Kb times log, and we'll call this the density of states final, minus Kb times the log, the density of the states initial. And remember, if you subtract 2 logarithms from each other, that's the same thing as the logarithm of the ratio. So this, and this is pretty important here, this is Kb log density of states final over density of states initial. Okay, and we're assuming that if it's an ideal gas, each molecule can move independently of each of the others. So we could write this as Kb log density of states final for each molecule to the n, where n is the number of molecules, and delta omega initial per molecule to the n as well. Right, because the ideal molecules don't see each other. So we can write this as Kb log final density of states for each molecule, and initial for each molecule to the n, right? Because we could just gather the terms there. And that's going to be equal to n Kb log of the final possible configurations per molecule and the initial configurations per molecule. Okay, so we've got it simplified. All we need to figure out is how many more states each molecule has at the end of the process versus at the beginning of the process. Well, each individual molecule has 5 times as much space to move around it, right? The volume has gone from 2 to 10. And so this just ends up being NKB log of 10 over 2 NKB log of 5. So we can plug that right in. Now it's 0.08 moles times 8.31 joules per mole Kelvin. And what's the log of 5? It's 1.61. So this is equal to 1.007 joules per mole Kelvin. So what we essentially have is a formula of the change in entropy of a gas, of an ideal gas, which most gases you can treat roughly as ideal, is going to be NKB log of volume final over volume initial, which is really amazingly simple, right? This is a really simple formula coming from like trying to count up all the possible ways for the molecules to be arranged. So if we look at the change in entropy in the reverse direction, delta S, if it's going, equals KB log V final minus V initial. If we have the same gas and it's going, now the final is 2 and the initial is 10, that will be KB log, final is 2, initial is 10, that will be KB log 1/5. But of course, the log of 1 over something is just the same thing as negative KB log 5. So in this case, it would be negative 1.07 joules per mole Kelvin, which is what we'd expect, that the entropy change in one direction is exactly minus the entropy change in the other direction. So there's a lot of, for many changes, it's very hard to calculate the entropy. For gases, if you treat them as ideal gases, which is usually correct, you can get highly accurate entropy estimates just from thinking through the problem and coming up with a pretty straightforward formula. So that is the last slide for this segment, introducing entropy and how we can start to understand how to calculate entropy.